Hi, my name is Suhas. I am going to be talking about how to make CNNs work for non-visual data. Why is this important? Because in the finance industry and in healthcare, both of which I'm really invested in, a lot of the data that we have gigabytes and terabytes of data, but a lot of them are actually non-visual. And on the other hand, CNNs or convolutional neural networks have made great progress in doing a variety of machine learning and AI tasks for visual data, images and videos. And to some extent, there has to be some kind of a meeting point where we could use the power of and the advances of CNNs for non-visual data. This mirrors very closely to a talk that I given last year at an SBIE conference. I'm going to briefly talk about why this is different and why I want this to be a little different. But the route we're taking today is through surrogate modeling of these convolutional neural networks using decision trees to help understand the inner workings of these networks so that we know how best to apply these to data that's not traditionally meant for these sorts of networks. So as promised, the related talk was about transforming non-visual or tabular data into images for use in CNNs. That's a little different. What we're going for is trying to understand CNNs using tree ensemble techniques, for example, and try to redesign them, hopefully, to make them better for non-visual data. A caveat is in this talk, we don't talk about the redesigning aspect of it. We are localizing our energy to just understanding what happens. So in a sense, we're going to talk a lot about explainability. However, in the SBIE talk that I gave last year, I actually outlined two major routes of transforming non-visual data into an image data. One is a direct transformation. For example, you have a tabular data that has, let's say, 100 columns. Each column is a feature, and then it has 1,000,000 rows. Each row is an observation or a sample point or record. Now, each of these rows, which is a record, is transformed into one image. Let's say it's a 10 by 10 image or a 100 by 100 pixel image. Each of the feature, depending on what value it takes and how important that feature is allocated a certain number of pixels in this image. And not only is it a certain number, but also a certain location in the image. For example, a feature that's more important than everything else gets a larger share in the image. So we can look better at the small deviations in the values that an important feature takes. So that's the direct transformation. The other route that I outlined in the paper was something to do with GANs, or generative adversarial networks. What I did specifically was train pictures of, let's say, train GANs with pictures of, let's say, dogs or numbers. Or you can train it with anything, honestly. But let's imagine you're training a GAN with pictures of dogs. And you're doing something like an anomaly detection. So every time you convert a record, a numeric record from a tabular data set into an image of a dog that's generated by the generator in the GAN, a picture of a dog shows up where you have a financial, let's say, for example, a financial transaction or a wire transfer transaction. It's codified by a dog. What's interesting now is if there's an anomalous transaction, we can train the transformation networks such that the image that represents the anomalous transaction is a dog that looks funny. One example of that is a very cute dog without a tail, which ordinarily has a tail, or a dog with 3 legs. these are all examples. These are possible. Of course, you see dogs with no tails all the time. You see three-legged dogs, but they're not as common as regular four-legged dogs with tails. So anomalous transactions can happen, but they're not very likely. That is the point. However, you feel free to, there's a video link on the slide. There's also a paper link. Feel free to look at the paper, but we are taking a slightly different route on this talk. And instead, we want to understand the inner workings of a CNN so that we can hopefully modify it to work better for non-visual data. Broadly, I think the challenges with machine learning are threefold. They either fall into explainability, where we think just having the output is not enough. You might have a model that's extremely accurate, very high precision and recall, whatever metric you choose, but then we don't know why a particular prediction is being made. So in some sense, for us to actually understand, this happens a lot in physics, where you have a particular model that has great predictions, but you're really interested in deriving new insights and new theory. And just having the output does not satisfy that goal. So the problem of many models not being explainable or interpretable is one of the key challenges. And I guess that forms the crux of what we're going to be talking about today. On the other hand, you also have the problem with uncertainty quantification. Do we understand the uncertainty in the prediction behind the models that we have? And more importantly, can we quantify them? Once we quantify them, can we live with them? Now, different applications have different levels of uncertainty that we can live with. And again, that's a very subjective measure. Thirdly, one of the biggest challenges we have right now is data and quality of data. There had been an explosion of data, and we had this era called big data, which is slowly. I mean, it's big data is still there. We're collecting massive amounts of data, but it's not as much of a buzzword as it used to be. And now there are other things called lean models, where sometimes, for example, I recently consulted on a project where the researchers had to make estimates based on very sparse data for geological systems, specifically for predicting earthquakes, predicting a particular type of earthquakes, actually. And we didn't have a lot of data to begin with. So now you start pulling from the theory, not just from the data. And this leads to kind of a Bayesian estimation setup, where not everything is frequent as data-driven. However, some models really do need a lot of data to train, and generalizability is also a concern if you don't have that kind of data. And next is the data quality. How do we know that the data is reliable or it's not noisy? But again, that is not something we're going to be talking about. All right, so with that introduction, let's get into the anatomy of a convolutional neural network. Essentially, it boils down to this tiny little diagram at the top left. There are a lot of inputs, x1, x2, all the way to xn. So let's say we have n inputs. And all of these are pulled together into, let's say, a node or a neuron. Now, this is an artificial neuron characterized by two parameters, sigma and b. I'm going to get into what those are. And instead of just pulling in the values x1 through xn, we actually multiply them with weights w1 through wn. These weights kind of tell us not exactly how important x1 and x2 are, but how to scale them so that we understand. For example, if x1 is extremely small and x2 is a little on the bigger side, but they're equally important to make a decision. Now, in this case, x1 has to be scaled so that w1 x1 is approximately on the same scale as w2 x2. Now, this is not a requirement, but I'm saying if x1 and x2 are almost equally important, but they have vastly different values, that's how the scaling factor w1 and w2 become essential. Anyhow, we have this weighted scheme of inputs coming into the neuron, and then there is an output. Essentially, what the neuron does is it mimics a human neuron, where if the weighted sum of all the inputs that are coming in is beyond a particular threshold, then you have a firing in that neuron, and you have electricity that passes, and it conducts. So it forms something like a switch that gets turned on. So this part of the circuit is now active. However, this is not a step function typically, and we have different kinds of these what we call activation functions, which is essentially what sigma is. So sigma is an activation function that tells you what conditions does the input have to satisfy in order to trigger or fire this particular neuron. There are many popular choices for sigma. The most popular one is, I guess, ReLU, which stands for rectified linear units. And the other popular one is a hyperbolic tangent followed by a sigmoid. You can create your own activation function. So I'm going to talk a little more about it after a few slides, I think. And B is just a bias. So it's if you're an electrical engineer, you're going to call it maybe a DC offset or DC shift. It's essentially pulling the summation value of Wi xi up or down. So that's just a convenience tool. And if you look at the bottom right picture, you see a portion of a neural network. And so we saw one neuron in the top left. Now we have multiple neurons passing through multiple layers. Yk-1 is the k-first layer, and then it has, let's say, n neurons. And then there are n outputs. All of them go into the kth layer, and so on. So you have a propagation of those. So before we proceed, what exactly is convolution? The idea of convolution is, okay, if you're a signal processing person, you're going to realize it's not exactly the convolution from signal processing. It's similar, but it's not identical to it. All it is let's say, we'll demonstrate with an example, we extract a patch from an image. So let's say the values you see on the left, 0, 8, 2, 1, 172. Let's say these are all pixel values of a particular image that you've taken on your, let's say, iPhone. And let's extract a patch, the square patch at the center, 7264. And once we have this patch, we can convolve this with a kernel or a filter. Let's say our filter is 1, -2, 0, and 1. How do we know what this filter is? This is where the training comes in. When we train a neural network, these filter values are actually parameters that get filled out as part of the training process. But let's assume that we already have a kernel or a filter, and we have a patch upon which we are applying this filter. The way we convolve them is do a Hadamard product, which is like an element-wise multiplication. 7's multiplied by 1, 2's multiplied by -2, 6 by 0, and 4 by 1. So we get a Hadamard product, and then we take the summation of that. So 7 would be the final convolution result of this patch with this filter. And of course, it's a sliding window. So you take the next patch, you take a different filter maybe, or you take the same filter, and the process goes on. So after you've convolved an entire image with a set of convolutional filters, typically you get back an image that's approximately the same size. It's a little smaller because of the edge cases. the edges don't actually get filtered too well. But you could do some sort of a zero padding or whatever you want to do. You could potentially get an image out that's the same size as the input image. And then there's pooling. Pooling is a very common feature that's used in CNNs. Essentially what it does is let's split this image on the left into 4 different quadrants. I've ordered them by color. And what we want to do is we want to represent all of these green pixels, 0, 8, 1, 7, exactly by 1 pixel. So we want to make a representation. And all the blue pixels by 1 blue pixel, and so on. So there are different ways to pool. You can do max pooling, min pooling, or mean pooling, or any other different type of pooling. I'll just give you an example with max pooling. You look at all the green pixels and you identify the maximum value of those pixels, and that would be the representative pixel of that entire green block. And you do that for blue, red, and yellow. And the idea behind pooling is to reduce dimensionality, and it also has good properties like inducing shift invariance. So the question is, to understand these CNNs better so we can apply them to financial or healthcare tabular data sets, can we build decision trees that mimic these neural networks? Why decision trees? Because people understand them. There are a series of if-else statements, and in finance and healthcare, practitioners have been using decision trees, ensemble methods, random forest, gradient boosting for quite some time now, and we understand how they work. So in the process of creating these surrogate models, how much generalizability do we lose? Do we gain any insights? So we're going to just look into these questions over the next few slides. But we're going to get started with how do we model exactly one neuron with the decision tree, and then we can extend this concept to an entire layer of neurons, and then we can create an entire neural network using decision trees. But let's look at one neuron first. So this is the same exact image from a couple of slides ago. And what we're going to do is we're going to take the products x1, w1, x2, w2, and all the way. So these are the weighted inputs, and we're going to sort them in descending order. And once we do that, we're going to redefine the variables. We're going to call, let's say, w1, x1 is, we're going to just represent that saying it's v1, just for simplicity. Now, let's say we have a sigma function that's something like a step function. What we want to know is if whatever is in the argument, the parentheses, b plus the summation of wi xi, if that's bigger than a particular value, the neuron's going to fire. If that's smaller than or equal to a particular value, the neuron's not going to fire. So we want to figure out, let's say, since we have made a descending sort of this, if v1, which is the highest input value along with its weight, if that's bigger than minus b. Why minus b? Because we have a bias term of b inside the argument. If it is, we don't need to do any more computation. We can approximate the happenings of this neuron by the function just below, which is sigma of b plus v1 plus c of n minus 1. Essentially what it's doing is it's approximating the value of all the other inputs other than x1 through a constant. Assuming it's a constant, it doesn't matter too much because we have already achieved the minimum threshold for the neuron to fire just by using one input. Let's say it's x1. Regardless of what the other inputs are, it doesn't really matter. And we are of course assuming these are positive numbers. So once you have a particular value, the cumulative sum is never going to reduce. Now, once we have a decision tree for a single neuron, we can model for different neurons, an entire layer. Now, let's say there's layer yk and we're planning to go to layer yk plus 1 in our neural network. And I'm going to represent tk to be the decision tree which translates the kth layer into the k plus first layer. You could do the same thing for convolution, but now we don't even need an entire decision tree, we just need a decision stump. A decision stump is essentially a decision tree that has only one layer in it. It's a really short decision tree. And for example, convolution, which is represented below, is equivalent to, I'm not going to prove this in this talk, but it's equivalent to this decision tree on the right, where you ask the question, is the Hadamard product of the patch and the filter, when you take the sum of the Hadamard product, is that bigger than 0? Yes or no? And depending on that, the value is assigned. And so this decision stump replaces the convolution activity in a neural network. You could do the same thing for pooling. The interesting thing for pooling is that pooling always reduces dimensionality. And because we want these trees to be functions from Rn to Rn, that just makes math simple. So we have, a bunch of layers in the neural network is now represented by a bunch of decision trees, one followed by another. If one decision tree is an Rn by Rn transform, and the next decision tree is an Rn by R1 transform, and the next one is an Rp by Rn transform, it just doesn't make sense, because these are staged together, these are chained together. So in order to make these transforms easier, we want to maintain an Rn by Rn transformation for all of these trees. And so even though pooling reduces dimensionality, we're still going to treat it as a full dimensional output, except that where the values are no longer relevant, where the dimensions are gone, we gray them out. So when you see the pooling layer in the image, you see some of the neurons being grayed out. And we intentionally set negative values to these so that even though we keep an Rn by Rn transform, we understand that these values don't actually have any meaning anymore because we've reduced the dimension. However, we also have a decision stump for pooling. Now, we have a sequence of decision trees that take you from one layer of the neural network to another. And let's say we start with neuron 1 of layer 1, which is represented by a decision tree, and then we go to neuron 1 of layer 2, and then we go to neuron 1 of layer 3, so we have a string of these decision trees. This is again a representation of what I just said. So there are different types of trees. If you see the picture on the right, which is an equivalent representation of the neural network on the left, you see three types of trees. The green one, the yellow one, the blue one. The green one is the tree that represents a neuron, and the yellow one is the one that represents a convolution operation, and the blue one represents a pooling operation. You might not have all of them, but sometimes you might just have a subset. But it's good from a general representability point of view to just show all of them together. And now you have a very complex but easily understandable decision tree sequence of these neurons in every single layer. And you stage them together, and then you go from the input of the neural network to the final prediction. And now all the neurons, all the convolutions, all the pooling, they're all replaced by simple if-else statements. All right, so now what? We replace everything with if-else statements. You have simple nodes instead of neurons. But what do we do with this? One example, this is not an end-all, but one example would be something like using, Shapley values. Shapley is a very popular explainability tool used in, it could be used for a lot of different estimators, but they're very popular especially for tree ensemble methods. And there are other options called kernel SHAP, which could be used for other kernels, but I'm not going to get into that. For those of you who are not familiar with Shapley, I just want to give you an example. So now, let's say we have an algorithm that that's based on a prediction based on football. So let's say you have the number of goals scored, ball possessions, offsides, blocked, and how many on targets, corners, and now we finally have an output value, which might be the probability of who's going to win the game based on previous statistics, or it could also be a case where what factor led to the to a victory, or what was the most important factor in the defeat of this team. So if you look at the graph above, if you look at the picture, there are some red features and there are some blue features, and the red ones actually contributed to pulling the output value high. So let's say the prediction is this team going to win? And 1 being yes and 0 being no, and then there's a threshold in between. Let's assume the threshold is 0.5. And if any output score bigger than 0.5, you're going to predict that the team's going to win. Now, in this example, the value is 0.7. And what it tells you is the factor that contributed the most to it is that this team scored 2 goals in the previous match, in the previous game. The factor that took away from it, the factors that actually made the prediction that the team's not going to win, are having ball possessions at 38%, or having offsides, or that they got blocked twice. So there are different factors, and Shapley provides a way of understanding how important these factors are. Why is this important? Because now we have reduced, if you go back to the slide, we've reduced an entire CNN into a set of decision trees. And now with these decision trees, we can analyze individual factors or individual columns or features in your data set and tell them, okay, this is actually what's causing it to be, for the algorithm to make these predictions, for the algorithm to behave the way it is. And explaining these is much easier on decision trees than it is on neural networks. So that is what we've tried to achieve using the surrogate models. And once we understand that these are the factors that actually make a lot of sense, and these are the ones that are not so important, we can feed them back to construct a neural network or a CNN that works better for this particular data set. That is my hope for step 2. This talk is not about that. It's a precursor which could lead to that idea. There are some, I just want to show one example before I conclude. I just want to talk about image-to-image networks and adversarial attacks on them. So when you have an image-to-image network, you're doing something like denoising of an image or tomography, microscopy, super resolution. Typically use something called a UNet. And in our studies, we have successfully ported UNets onto surrogate ensemble models using decision trees. You could also use them for image-to-class networks, where you have an image and you're trying to classify what that image represents. Here's an example. Here's a famous adversarial attack from, this was published by OpenAI. So the image you see is actually a panda. It's obviously a panda, and we humans understand that. But when you add a very little noise to it, the algorithm that correctly identified it as a panda all of a sudden, with a very high confidence, thinks it's a gibbon. A gibbon is a monkey that looks like this on the right. So for a human classifier, we understand a panda is very different from a gibbon. But adding very little noise, we don't understand why it should tip the whole algorithm from predicting it to be a panda to predicting it to be a gibbon. Unless we identify what's actually going on. I mean, what the heck is the problem with it? I don't think these convolutional neural networks are going to be ready for essential financial and health applications. So we looked at it, and based on porting this entire CNN into a series of decision trees, we understood that the red box you see on the panda's face here, that red box actually accounts for 35% of the decision making. And if you look at the equivalent portion, the part of that red box in the gibbon's face, now you can sort of understand why it could be confusing for the algorithm when something minute changes. Now, the way to fix this is to make sure that there is not one of those tiny red boxes which accounts for 35% of decision making. That has to change. And these are the insights that will make CNNs a robust choice for healthcare or financial data sets. And that is what I wanted to show you today. Thank you so much. And I'd be happy to answer any questions.